I will not make the complete list of superheroes, but you can grab in the list and see what happened to some of them. But the very more interesting point is that for this edition, one of our superheroes is a former participant. Here is someone that now takes part of the short list of people who has already given one course and is given another course at Paraty, something that Steve is also making this upgrade to the list of twice as a lecturer in Paraty. But Fernando Brandão is really an old friend that will tell you that he was part of the Paraty events in 2009, etc. But it's important to say that this guy comes from Belo Horizonte and has made all his career that you can check in details, all the places he has been an important guy in making interesting results. And at the same time is this simple and very nice, easygoing guy. And unfortunately, very going in the sense that he will stay here with us only tomorrow, today and tomorrow. So please do not be shy, interact with him as much as you can during these 2 days. Of course, giving some time for him to also work in whatever else he needs to work. But it's true, enjoy not only the course, of course, the course you have to take good questions, please do your job. But please also take the advantage of being together with Fernando for those 2 days, and please Fernando, take stage.
Thank you, Marcelo. Thanks a lot for the introduction. Hi everyone, I'm very happy to be here. So this morning you heard from Nair, right, and then from Steve, and both of them were talking about Minas Gerais, right, that maybe some of you know, and from UFMG, I'm also from there. I was a colleague of Nair actually when we were in our undergraduate studies. Then, and I also, let me talk about my Paraty story. So I came first time 2009, the second edition. Can you get some echo or? No?
Yes.
Okay.
Speak closer.
But you can speak closer to this. I need a mic because of the recording of this. The problem is that I scream usually when I speak, so with mics not so good, but I'll try my best. And so then I was a postdoc back then, but again, it was great. I think I was in the workshop, couldn't come to school. Then as Marcelo said, I was teaching here in 2015, and back then I was interested in, this is bad. I was interested in quantum thermodynamics. I was teaching about that. Since then, I started doing something slightly different. So now, just tell you where I am. I work for Amazon. So Amazon they make packages, right? So there is also something that they do that maybe is well less known, but it's also interesting, which is a cloud service, right? So they were the pioneers of the cloud. So they do a lot of cloud computing, right? So many big companies use them for cloud computing. And because of that, they got interested in quantum computing, right? So one day, maybe, if you can figure out the technology to offer quantum computing in the cloud as well. So that's, so I work with a team of people, right, to try to build a quantum computer one day. And we use superconducting qubits. That's why, we tell you about quantum computing, error correction with superconducting qubits. And I'm a professor at Caltech. So just a second, I want to check. Okay. So I'll be telling you about quantum error correction and in particular how to do this with superconducting qubits. Today will be mostly quantum error correction in general. I'll just tell you some general ideas how you can do quantum error correction and why you have to do it when you have qubits which are on a spread edge, like in a plane, and then in the next lecture we connect, right, why the superconducting qubits can be one of the ways of realizing this. Please ask questions during the presentation. Okay. So just to start, quantum computing, right? Why it's exciting? What you want to do? You want to explore the intricate physical laws of the microscopic world to perform computation in novel and improved ways, right? So it's kind of remarkable, right, that we have computer science is so successful, right, and it really changed our work, right, in the last century, and that is not the right computer science that we do so far, right? Because, you know, like if it's a science, it has to be something about the fundamentals, right? And the fundamentals is like quantum computer science, right? So, and maybe it will be the same kind of computational paradigm, but it's not. It's very different, right? So that's realization that, you know, was that some of the pioneers did like 40 years ago, and it's very, very exciting, right? So it's really this like new science and, you know, crossover of physics and computer science, and I think we're just in the beginning. So there is definitely potential for a new paradigm in computing, right? But there is still a long way to go, right? So, and why that's the case? Because there is very hard scientific and engineering challenge if you want to actually build a quantum computer, right? Or build quantum hardware at scale, which, you know, would allow us to really do interesting computational stuff. And I'll explain why, right? And there's also another thing that, you know, we should know is that we want to build these quantum computers, right? And they're great, they're very exciting, and we have, you know, some reasons why we want to build them. But, you know, probably there are way more reasons why we want to build them, right? So in terms of like the best application for quantum computers, we don't know them either, right? So that's also a very interesting research question. There's a lot of research going on. Progress is not very easy, right? Because we don't have quantum hardware yet. But it's also, you know, something that if you think if you think it's exciting, it's a very good area to go work, is quantum algorithms, which I will not cover in this lecture, right? So, but I want to mention anyway. Quantum technology we talk about these days, right? And we want to build future quantum technologies. But quantum mechanics has already been very useful for, you know, quantum for technologies from last century, right? So NMR is an example, right? We have to understand, you know, quantum mechanics of molecules. Laser, of course, right? Needs to understand, right, quantum optics, and even the transistor, right? The building blocks of the bits of the computer, right? All the computers that we use today, right? We really have to develop like solid state quantum physics to understand how it works. So that's great, right? But they are not really quantum technologies how we understand them today, right? Because in this you know, technological advances, we understood quantum mechanics just kind of to be able to ignore the quantum features of the device, right? And to operate in a very fast way, right? And that's not what we want to do now. Now we really want to take the most interesting and weird behavior of quantum mechanics, right? Like, you know, superposition, entanglement, interference, and make them to our advantage, right? When we build some technological applications. So it's really the next step, and of course it's way harder, right? Because we want to explore kind of, in a sense, you know, the boundaries of quantum mechanics, right? Pushing on the direction of like complexity, right? If you want. Now, what is a clue that, you know, it's worthwhile to build a quantum computer, and that it would be a computational model more powerful than classical computers? This came really just from the experience of, you know, the whole physics community. Once we started to do numerical physics, and we started to do numerical physics with large quantum systems, right? So, for example, a system of many electrons, right, with some, you know, condensed matter experiment, or a system of many photons, and so on. So one way to see this is just this plot that many people use, right? Maybe you already seen this a few times. But this is the Department of Energy of the US in this case. It has a few supercomputers, and let's see if I can. Okay. And here's better. And it just every year it puts a list of, you know, all the areas that it allows the use of its supercomputers, and then, you know, by how much, right, of the share of the supercomputer it has allowed. And so you see, okay, Earth environmental science is the most. Then there's chemistry. Chemistry, there's most of chemistry, like quantum chemistry, right? So there's a lot of like simulating large quantum mechanical systems, like large molecules. Then fusion energy, then material science, there is also quantum mechanics, right? Then nuclear physics, again, high energy physics, right? Like a plasma with, like, you know, quarks and gluons, right? This kind of stuff. So a large fraction, right, of you know, supercomputers worldwide, they are devoted to simulating quantum systems, right? And very roughly, this is because the cost grows exponentially with the size of the system, right? So if you think about the wave function, right, Schrodinger equation, if you put one more spin half system there, you have to double, right, the Hilbert space, and each time then you multiply by 2. Do you always have to do this kind of naive way? No, right? But actually, for many systems, we don't know ways much better than that. So then, if you want to simulate, you need 2 to the n steps to simulate a system of n qubits, right, of electron, photons, etc. And that's, of course, because of the entanglement, right, that we have between the qubits. So very quickly, it becomes prohibitive to do the simulation, right? So if you want to simulate 30 qubits, it's 16 gigabytes, that's okay. 40 qubits is 16 terabytes, it's okay, you have to push. 50 qubits, 16 petabytes, it's, you need a supercomputer, right? I have to find the right supercomputer. SQ has 333 qubits, it stands to the 100, so no way, right? You have to be able to store this wave function. So of course, there's clever ways of doing classical methods, and there's a lot of people who do that, but that points out, right, that maybe we shouldn't use classical computers to simulate quantum systems, right? So, and there was, I think, 2 people who first realized that, right? There was David Deutsch, he has his own motivations about interpretation of quantum mechanics, right, for thinking about the idea of doing computation with quantum mechanical systems. But there was also Richard Feynman, and he gave this lecture simulating physics with computers in 81, right, so 42 years ago already. And then he said the following, like, there was this nice quote, he said, trying to find a computer simulation of physics seems to me to be an excellent problem to follow out. Nature isn't classical dynamics, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golden, it's a wonderful problem because it doesn't look so easy. So, right, so he had the insight, okay, so why not, right, build a quantum computer for simulating quantum mechanical systems, because it seems the classical mechanical systems are not so good at it. And he even had this insight, okay, it's kind of exciting because it looks pretty hard to do it, right? So, and he was right on both right of his insights. So that's where we want to be in this century, hopefully, right? We want to build the next stage of this quantum technology. Of course, I won't cover in this lecture, right, but there is, of course, quantum communication, quantum cryptography, quantum sensing, right? They are all exciting stuff. I'll just cover computation here and just one aspect of computation. But what we want to do, quantum computing is about using well-controlled quantum systems for computation, right? And it's pretty easy to just start from what we do classically. We have been doing for a long time and quantize it, right? It's a very direct recipe, right? So I think many of you already saw what a quantum circuit is, but I just want to mention to recap. So we start with like how our computers are built, right? On the lowest level, we have these transistors, and on these transistors they store a 0 or 1, that's a bit, and then you apply very simple operations on these bits, which is these logical gates, right? So this is, for example, an AND gate. You have 2 bits, and then the gate computes the product. You can have an OR gate, which computes the sum modulo 2, and then if you just compose all these gates, which acts on 1 or 2 bits at a time, a large number of them, where very long depth, then you can compute very complex functions, right? In this case, it's still not a very complex function, right? But it's supposed to keep iterating them along a lot of them. Then you can compute, make very interesting computation, and that's what our computers do, right? At the most basic level. Now, suppose we want to do it quantum mechanics. Then we have to change one thing first. Well, everything has to be reversible, of course, right? Because Schrödinger equation leads to unitary dynamics, and that's reversible. If there is no noise, later we introduce noise. But now, so that's fine. There is also ways to do classical computation reversible, right? So that's not such a big difference. But what is the big difference is that now we have a much richer set of gates, right? We just have the gates of bits, they are very restricted. But now we have qubits, it's a 2-dimensional quantum system, like a spin-half particle, for example. And now we can make any unitary on a single qubit. So any unitary, any like a 2x2 unitary matrix, right? This example is the Hadamard matrix, I'll tell you what it is later. And we can also make operations on 2 or 3 on a few qubits at a time. And they are very important because without them, the qubits don't interact, right? So you need the qubits to talk to each other to do something interesting. In this case, we have it's called CC gates, conditional on this case of the first qubit being 1, you put a phase of -1 on the second one. It's like a cousin of the CMOS gates. And here you see a very simple circuit, right? If you just compose this basic operations, you prepare the exact state of 3 parts. And then you can keep applying more gates, more complex gates, right? More complex algorithms, right? And then just do an interesting computation. And then the question is, can you do that in a way that really leads to interesting computations of problems that we care about? And the answer is yes, right? And there was some, I'll mention a little bit later, but that's the reason why we want to build a quantum computer, right? So we can just come up with interesting circuits that we draw on the boards these days, right? Because we don't have the computer, and we can prove, right, that they solve interesting problems that we like to solve. Any questions so far? Okay. Right. So then going to the closer to what we cover in these lectures. How we actually want to build this quantum computer, right? So I talked abstractly to you about qubits, right, and gates and so on, but then we need a physical implementation for them, right? So when I talk about a qubit, now I have to tell you, this this two-level quantum system is implemented in a photon, the polarization of a photon, right? Or in the spin of the electron of atom, things like this, right? And there's many ways of building a quantum computer. These are just some examples, and each one has their preference, of course, right? It usually depends where they come from. It's very hard to know which one is the most promising right now, and that's why there's research in all of them that should continue, I think. But right, we have to make progress, so we have to usually, if you want to work one of them, you have to pick one of them and just develop, right, and see where it ends. So as I mentioned, I will be covering this called superconducting qubits. So they are very interesting, and I started working on them not so long ago, maybe like 5 years ago, but it's been interesting. So it's very so the way to think about them, and I'll tell you way more about them next lecture, but I just want to mention a few words. Is that suppose you have electrical circuits, right, that we learned in school. So we have a LC circuit, for example. So we have an inductor and we have a capacitor, right? Usually we have a resistor as well, but suppose that we use a superconductor, right? And that's the reason for the name for all the wires, which we know exists at sufficiently low temperature, right? Then there is no resistance. Then these LC circuits, right? If you see the current there, this will be what? This will be like a sine or a cosine, right? It's just now suppose we just cool it down below this critical temperature of the superconducting state, even much cooler, like 20 millikelvin, for example. Then what will happen is that the energy levels get quantized, right? Like Landau levels, right? So and then you have like a harmonic oscillator, right? So this harmonic oscillator has like these equally spaced levels, and you can think, maybe that can be used as a qubit, right? Just use two of them, and you go 0, 1 in the first two, for example. And why that's nice? Well, because once you look at the frequency that you get, if you just create this kind of LC circuits on some, for example, silicon plane, right? You can use aluminum to do them. Then you see that the resonance frequency is in the microwave range, and that's nice. It's in the microwave range because then you can just use everything that has been developed for microwave, right, to operate the qubits, to send signals to the qubits. But now if you set a signal to try to couple the first two levels, all levels will be coupled, right? Because they're equally spaced. So you need a new thing, which is called a Josephson junction. That's a non-linear element, right? It's also, Josephson got a Nobel Prize for it. Basically, you put two superconducting islands and you put the insulator in between, and then pairs of Cooper pairs can hop from one to the other. And if you add this to your circuit, you get a non-linear oscillator. So the energy levels, they are not the same anymore, and then you can use the first two levels for qubits. So I'll tell more about this later. So many people are developing this, many companies as well, right? So IBM is doing it, Google is doing it, Amazon is doing it, Alibaba is doing it, many academic groups, of course, and it's relatively new if you compare to these ones, except Rubber atoms, right? So I think this started like 2008, and the quality of the qubits and of the gates have been progressing fast, and I'll tell you more about this later as well. So some of us believe that this is a possible way of building a scalable quantum computer, very remains to be seen. Then there is like really, the first technology that was considered for really building a quantum computer in a serious way, right? Trapped ions. You just have a linear trap, for example. There is other ways, but a linear trap, you put some, electromagnetic fields here, and then you put ions, and of course they are going to try to repel each other, right? They are all the same, but because of the other electromagnetic field that you put here, they arrange, they form a line, for example. And then there is this line, but if you move one of them, the other will move as well, right? Because they are all of the same type. So then they have an interaction between them, and you use this interaction for doing the gates. Where the qubits, they lie in the electronic state of the ions, right? You choose just two levels electronic states, and then that's kind of obstacle. That's like you use a laser for doing the transition between these two levels. This defines kind of the 1 qubit logical gates, and the movement defines the 2 qubit gates. So this being, I think, like, the first experimental results is more than 25 years old, maybe something like this. So it's been going for a long time. You can get very good results on a few ions. Scaling them up is been showing difficult as everything else, right? But also, few companies work on that, like Honeywell. There is also some startups like IonQ, and of course there's people, right? There's people that you work on that for a long time in academia, right? In Innsbruck and in the US and so on. Then this is like Rydberg atoms. It's a cousin of this one. Here you use a neutral atom, but then you use what you call a Rydberg level, right? Which is a highly excited level, which is strongly coupled with other Rydberg levels. And then the way you have like two metastable states, they don't couple to anything, it's the qubits. Once you do the Rydberg atom, it strongly interacts with the vapor. Also drops pretty quickly, so only someone that is very close will interact with it. And then this way you can do the gates and so on. What is nice is that you can create some traps called tweezers, up to tweezers, and they just move them around any way you want. You can like create Eiffel Tower, for example, like here. And it has been very, very fast progress on the Rydberg atoms. Also on error correction, which I won't cover, but I want to mention. So this, I think, is a very interesting, more novel way of doing quantum error correction, and I'm kind of excited about this too. And yeah, we can talk more if you ask, but I think for like in terms of using atoms, probably this will be the best. And of course, you can use photonics, right? Also on a chip, and there's some companies that do it. There's some many academic groups, and aligns with what Cyril was telling us about before as well. So here it's interesting photons, right? They don't decohere a lot, right? So once you create them, they are there. It's great. Of course, to make them interact is difficult, and there's interesting ways of doing that. Using also ideas from error correction for doing it efficiently. But I won't talk much about it. So I just want to tell you this slide that there's many ways of doing quantum computation experimentally and doing error correction, and in all of them we have been seeing a lot of progress and a lot of work on implementing quantum error correction. It's still a long way to go, but they are all interesting platforms. Now, why we want to do quantum computing? There's some applications that we know, right? Before I mentioned, we don't know anything. We know some things, right? Of course, there's many caveats and there's many details that I don't want to tell you. The first application that really got everyone excited was when Peter showed us in '94, right? That you can factor numbers efficiently on a quantum computer, and therefore create RSA, which is the public key crypto system that we all use right today. If you want to break RSA with 2048 digits, which is the scheme that we use today, when we use our mobile, for example. Using Shor's algorithm, we need 6,000 qubits for that, so it's not so bad, right? 6,000 qubits could already break, like the most important cryptographic protocol. What it can do is 6,000 bits, not a lot, right? So that's maybe that's good. Then in physics, in chemistry, going back to this vision of Feynman, there is many things you can do, right? Many applications you can do, like simulating interesting materials, right? So for example, if you want to simulate this chemical molecule, which is an interesting molecule that appears like if you understand the nitrogenesis like process that happens in ammonia, you need like around 200 qubits, something like this. So also small number of qubits, you could do some interesting chemistry. Material science, right? Maybe you can simulate some Hubbard model that you think can shed some light into high system conductors, right? So stuff of this form. Also, a few dozen qubits, you could already start doing something that is not possible. Oh, sorry, there's a question.
Yeah. Just a quick question: is it qubits or logical qubits?
Right, we will get to that. Yes, so there'll be the punchline of the slide. Yeah. So for now, it's just qubits, right? But no, there's the sketch. It's perfect qubits, right? So if I was giving perfect qubits, right, I could go off this. And you can do, you'll be, so I didn't mention here how big is the speed up, right? So this can all be like exponential speed ups. The quantum algorithm can run exponentially faster than the best class algorithm that we have. Sometimes we have like a lot speed up for a large number of problems, but they're smaller speed ups. They're like quadratic speed ups and so on, and they have to be careful. It really they're meaningful. But then for scheduling, ranking, learning, searching, right, all these kind of things, you can do application optimization. And if you also have a few hundred perfect qubits, you could do it. But that's the catch, right? So perfect qubits. And right? We haven't seen a perfect qubit yet, right? So why? Because quantum systems already interact with the environment, right? So there's already coherence in the system, right? Nadia was telling us about in her lecture, right? In how we can address like an open quantum system, right? And quantum computation is all about this, right? They always have this open quantum system, and you're trying to mitigate the noise from the environment as much as you can. So let me jump this. So we have to compute with imperfect qubits, right? That's the reality, right? There's no perfect qubits. So let's take as an example if you want to factor a 2048 digit number, right? Because we want to break RSA. Then, as I mentioned, this requires using the most optimized version of short algorithm that we know today, 6,000 qubits, and requires a quantum circuit of depth 10 to the 7, so 10 million depth, right? So depth is like, of course, you can do gates in parallel, then you parallelize as much as you can, and then how many rounds of gates you have, that's the depth of the circuit. So you need 10 million depth. So you see, right? So to do something as interesting as spectral number, exponentially faster than the best classical algorithm, well, you can do quantum mechanics, and that's kind of very exciting, right? But it's a very complex algorithm, right? As it should be. So now if you just think about that, you have 6,000 qubits, you have a circuit of depth 10 to the 7, you want to have a small error in the end. It's okay if you have a small error on each gate, right? So quantum mechanics is linear, right? And that's very helpful. So the errors in the gate, they just add up, right? Nothing worse than that happens. But you have a lot of places for errors, right? So you do need error rates of the order of 10 to the minus 12 for this to work, right? So you can't use imperfect gates or qubits, but you need extremely small error rates, right? If you really want to run the interesting applications. And if you look at what we can do today, like what is the 2-qubit error rates in the lab, in any of these kind of platforms that I mentioned today, of course they vary depending on how good of experimentalist you are, maybe, but also depending if you want to do a larger circuit or a smaller circuit, right? Stuff like this. They range from like 1% to 10 to the minus 3, 0.1%, right? So you see a huge gap, right? So we have to reach 9 orders of magnitudes if you want to go from what we can do today to where the interesting applications are, right? Of course, we can find new applications. That's another possibility, right? But it's not where I want to cover here. So the problem that I want to cover in this lecture is how to bridge these 9 orders of magnitude, right? Which seems a very challenging problem, but that there is a solution on this. Any more questions? Okay. So how we do that? Okay, so there is only one way that we know of potentially doing that, which is not easy, but it's in principle it's possible. That's using this idea of error correction, right? Which is in the title of the talk. So that's the idea, which is a very old idea. It's a very successful idea classically. So first in classical computation, we do not use error correction just because the transistor is so good, right? The transistor, if you think about, this error rate is very small. The transistor is way smaller than this. I think it's like, maybe I'm wrong, so you have to Google it. But if I remember correctly, I think it's 10 to the minus 17. So, which is extremely low, right? So it's very surprising it's so good. So, we don't need for computation. But for example, whenever we communicate through an optical fiber, we have to use error correction because there's a lot of loss in the optical fiber. Whenever we store information in a hard drive, we use error correction, right? Because this hard drive, there is like loss there, there is error there is noise. So, error correction is a very established area of classical computing, right? And there's very sophisticated ways of doing error correction, but I want to start from the most basic one, which is called repetition code, right? So the idea is very simple. So suppose you want to store a bit in a hard drive, right? But the hard drive is lossy. How we think about a lossy hard drive? We just think that there is actually kind of a probabilistic process there, right? Which with some probability, P maps 0 to 1, and with some probability, 1 minus P leaves 0, right? You can also have the other process going from 1 to 0, and you have a probability Q of going from 1 to 0, right? And 1 minus Q, 1 doesn't change, right? So this defines a stochastic process, right? And the noise is, given by the stochastic process, right? If you do quantum mechanically, we go to what Nadia was explaining to us, right? Which is just, some completely positive resulting map, or just if there is some Markov linearity to some master equation, right? So there's like this noise in the process, and we wanna fight it, right? So how we can fight it? One way we can fight is just to decrease this kind of probability of error, right? Which we can do by isolating the system better, for example, or by sending a more accurate pulse, right? But this can only go so far. In error correction, you don't do that. You do a different strategy. You just try to correct for errors by introducing redundancy in the system. So for example, suppose you want to store a 0 in the hard drive, but instead of storing 1 0, you store 5 zeros. Okay, so I have a 0 I want to store, I will store 5 zeros instead. And this we can call a logical 0, right? So I just denote by this. And if you want to store a 1, you store 5 ones, right? So now you see you're using, there is 2 to the 5 different strings that you can have here, but only 2 of them have meaning, right? Only the all 0, 1 or the all 1 have meaning. And one logical bit, is constructed from 5 physical bits in this case. Now suppose you have your noise, and then your noise is assumption that we typically do. It can be relaxed a little bit, but it's important assumption. The noise is kind of independent from one bit to the other. There is a probability of flipping 0 to 1, probability flip in each one of them. Okay, but it's independent on one from the other. Then what was before the probability of going from 0 to 1? It was just p, right? But now, what is the probability that now what is the protocol that you use? After error has happened, you check the bit string here, and then you do a majority votes. Okay, you check how many zeros and how many 1 there is. If there is more zeros than 1, you say the logical bit is 0. If there is more 1s than 0, then you say the logical bit is 1. Okay, and now we want to understand what is the logical probability of error, right? What is the probability that actually you have a logical 0, but you think you have a logical 1, and vice versa, right? So now suppose we start from this. To really think that we have a logical 1, when I have a logical 0, how many bits we have to flip here? 3, right? Yeah, right, because this majority vote. And what is, and if the probability of each one of them to flip is p, right? Now the probability that 3 or more flips is of order p to the q, right? Of course, there's a prefactor, a combinatorial prefactor, right, which is not so big, but it's p to the q, right? So you see that the logical probability of error now is the q, right? Is taking the physical error rate to the power of 3, right? And of course, the physical error rate, for error correction to work has to be sufficiently small. But if it's sufficiently small, then you do get a gain, right? And then you can increase even more, the size of the code, and you get smaller and smaller probabilities of error. So, yes.
Why can I correct up to? I don't really understand what does it mean by correct up to 2 bit flips.
It means that suppose because this is called the decoding of the error correcting code is what is the process we are going to do to try to infer if there was errors and correct for them. So the decoding protocol is the following. So I check the bit stream, and then I see if there is more zeros or more ones. If there is more zeros, I say, it's a logical 0, so I just, and there is more ones, I say it's a logical 1.
I can see that, but you use like 5 physical bits to like encode 1.
Exactly. That's this redundancy, right? That happens in every error correcting code, right? So that's why you get this gain from you decrease the logical probability of error can be much smaller than the physical probability of error, because now for one logical error to happen, many physical errors have to happen, right? And because each one has a small probability of happening, the probability that many happen at the same time is smaller and smaller, right? It's high order. Any other question? Okay. So let me introduce some notation because it's going to be useful. So now, what is one way that we could actually, build a computer with a repetition code? By at least like it's a bit naive, but it's one idea. So we will have our, what we call the data qubits, right? These are the 5 bits here. They will be these white circles. So this data qubit 1, 2, 3, 4, 5. Okay. And then we either encode initially 0, 0, 0, 0, 0 there, or we encode 1, 1, 1, 1, right? But now we let error happen, and we like to infer, right? Basically, we like to do, we could use majority code that I mentioned. But let me show you a different way that you can, check for errors here. So suppose you use some extra bits, okay? These are called ancilla bits. So we have one ancilla bit between 1 and 2, A1, 2, between 1 between 2 and 3, A2, 3, 1 between 3 and 4, A3, 4, and so on. And we complete a very simple function on these ancilla bits, depending on the 2 data qubits that touch it. And the function is just this, right? It's just, OR, right, mod 2. So you just sum the 2 bits and complete mod 2. Now suppose that there is no errors, right? We have all 0 or all ones. Then, what will be the result on all of these ancillary bits? Who knows? Will be 0. No, it will be 0, right? Because if you have 2 zeros, 0 plus 0 is 0, right? Mod 2 doesn't change. Now if you have 2 1s, as will be here, then 1 plus 1 is 2, but 2 mod 2 is 0 again, right? So if there is no errors, all these ancillary bits, they will output 0 for you. So one way you could do error correction here is that you just compute this function and then you just check the value of this ancillary bits. If it's all 0, you say great, there was no error. Now suppose there was one error here on the data bit 3, right? And suppose we have all zeros here, and this one got flipped from 0 to 1. Then you get a 0 here, you get a 0 here, but what will you get here? Right, so this guy is a 0, but this one is a 1, right? So 0 plus 1, mod 2 is 1. So you get a 1 here. And you get a 1 here as well, right? So the two neighboring ancillary bits will tell you that there is an error here, right? They will both flip, and they say, oh, there's an error here. Great. What if there is 2 errors here on neighboring ones, on Z3 and Z4, right? Then you get a 0 here, you get a 1 here, you get a 0 here, right? Because it's 1, 1. But you get a 1 here. So now you know, oh, there were 2 errors on 3 and 4. And you can think about it, you see that this code can correct up to 2 errors, right? If it's more than the 2 errors, it cannot correct, it fails, but it can correct up to 2 errors. Great, so that's something that we're going to try to generalize for quantum now, right? So how we want to do error correction for quantum? It's surprising, right, that it can work, right? And many, when this kind of pioneers that I was mentioned before, right, for quantum computing, they start thinking about, right, the original ideas of our fields, and they discover quantum algorithms, and the first quantum algorithms. There was the skepticals, right, and some actually famous computer scientists, they were very skeptical, and they said this is never going to work, right? You don't understand anything about computing, right? Give up. And their argument was always something like, look, this quantum state is just some abstraction. We have this state vector, right, in this Hilbert space, and you need these amplitudes to have this very high accuracy in the amplitudes. And as soon as you have a little bit of noise, you will shift a little bit these amplitudes, right, very, very small amounts, and then the computation is completely destroyed, right? This is no different from analog computing. In analog computing, right, you want to do computing where you have kind of, for example, a particle in a box, but you require very high accuracy, right, over where it's in the box, right? And we know that it works in principle, it is very powerful, but once you have noise, it fails. And they said the same will happen with quantum. And then also Peter Shor actually was the first one who had the first insight, and many other people work on that, of course. Quantum is not at all like analog computing, and quantum error correction does work. And there is actually a simple reason to see why it's not so, it's more complicated, of course, than classical, but it's not so different, it's not like continuum, right, as people think. And this is what I want to show you in these slides. So first the question, is possible even in principle to do error correction? Here it's more complicated, of course, right? But the reason why it's not so bad is because really, once you think about errors in quantum systems, it's a little bit of simplification, but it's essentially true. There's only 2 types of errors that you can think about. So you have your qubits, right? The superposition of 0 and 1. Then one error that can happen on your qubits is a bit flip error, right? Where a 0 goes to 1 and a 1 goes to 0, right? Because everything has to be reversible. So that's a bit flip error, right? So later I'm going to introduce, but I already say now. So if you want to write this error using a matrix for it, right? A Pauli matrix, this would be an X error, right? So the X Pauli matrix applied to this guy gives this one, right? Great. Then there is another error, which is a very simple error as well, right? That we can all understand, which is uniquely quantum. So this is the only bit flip happens classically, of course, but now if you have a superposition, something else can happen, right? So the phase can change, right? The plus here can go into a minus, right? So this is called phase flip error, right? So just the weights are the same, the alpha and beta, but now it's a different space here. If you know the Pauli matrices, you can also express this error in terms of them, right? This is just the Z Pauli matrix applied to this guy gives this one, right? And great, these are two types of errors. What's remarkable about quantum mechanics is that these two errors and combination of these errors, meaning linear combination of these errors and a product of these errors, right? If you combine both of them, you have bit flip and a phase flip at the same time. This really is all errors that can happen on the qubits, right? So this idea that there's like this infinitely many different types of error. I mean, of course, you can think about that, and it's a way to think about that, but it's not the correct way for error correction. So we should think that there is bit flip happening there with some probability. There is phase flip happening there with some probability. And of course, there is phase flip and bit flip happening at the same time, right? Some probability. And that's it, right? But why that's the case, right? Because as Nadia showed us in the morning, so you can have this stochastic process, which is a completely positive method. You can have this Prowse operator there, right? And this Prowse operator, as long as you satisfy the condition for being completely positive, right? Which is sum of its conjugate times itself equals identity. It can be anything, right? But there is one. This happens for one interesting thing, which is the Pauli basis, right? Which is x and z and x times z, which is y after base. They form a basis of operators for qubits, right? And product of Pauli bases form a base of operators for n qubits. So any error that you have, in your process, right, which is just some arbitrary Prowse operator, can be decomposed as linear combinations of bit flip, phase flips, and bit flips and phase flips at the same time. So if you can correct each one of them, which error correction tries to do that, right, quantumly, then you can correct all the terms in the superposition, and you can correct this arbitrary, right, kind of Prowse operator data. So that's a massive simplification, right? So now it's more complicated, but now instead of only having to correct bit flips, we have to correct bit flips and phase flips at the same time, right? So that's the challenge that we have here. Any questions here? Fine. Right, so let me show you one way that we can do it. So you can think maybe this, so the one way you can do it, you can think that this is analog of the repetition code in the sense, and I'll explain why. But also it's interesting that unlike the repetition code, right, which is really almost never used in classical computing and when you do storage and communication because there are way better codes, surface code, we really think that, as far as we know, that's still the best codes that we have today for building quantum computers. And many of the experiments people doing use surface codes, and I want to, basically, use them throughout this lecture. And why? Well, first because I'll tell you later, it has good properties in the sense that it can correct like a lot of errors, right? But in a very physical, in a physically favorable layout, right? So all your qubits, and I'll explain what these qubits are in analogy to the repetition code. They're on a plane, and you only have interactions between near stables, right? And that's good, right? Many of these platforms that I mentioned, they is what they can do, right? So you can, if you want two qubits to talk, for superconducting qubits, for example, they're considering, you should put a capacitor between them, right? That's the way to make them talk, right? But it's hard to put a capacitor between two qubits which are far away, right? So this naturally leads to this kind of two-dimensional layout. And the surface code, is in 2 dimensions, so that's nice. Of course, there's surface code in other dimensions as well, but there's a 2-dimensional. So let me let's take the so now let me explain how it works. Let's take the first row here, okay? This first row, and now ignore. So now as in the repetition codes, the data qubits, the qubits where the logic qubit really lives, these will be these white circles. Okay, so these white circles. So this is a surface code. Surface code actually is a family of codes, and we have a parameter that is called the distance, or letter d, and this tells how big the code is. And when distance grows, it can correct more and more errors, and of course use more qubits. But the performance of the logic qubit should improve. Right? This is something that I'll try to show you. So in this case, I'm putting here distance 5 surface code. So if you count the number of data qubits in each line is 5, the number of data qubits in each column is 5 as well, right? So it's a 5 by 5, square lattice of data qubits. Of course, these ancillary qubits that I put for the repetition code maybe we thought it was a luxury, right? Because we didn't really have to use them, right, to define how to do the computation, and that's true. In quantum computation or in quantum error correction, these oscillar qubits, they are a necessity, right? There is no way to do error correction without them. And that's because another thing that is different, right, quantum from classical is that quantum, if you observe your